Mesoamerica was a cultural region that stretched between southern Mexico and Central America. They developed a very sophisticated mathematical process, which they used for astronomy, architecture, calendar systems, and many other purposes. In this picture, you see an Aztec calendar and a Mayan pyramid. These are two different groups of people who spoke different languages, yet they shared a similar civilization, which utilized similar concepts like mathematics and calendars. This can be compared to how Europeans speak different languages, yet use similar systems, and they belong to the same civilization. Incredibly, the indigenous people of Mesoamerica only utilized three symbols for their mathematics: a dot, a bar, and a shell. The dot equals 1, the bar equals 5, and the shell equals 0. It is said that the ancient Mexicans were the first to use the zero. Throughout the world, they were the first people to utilize the zero within complex mathematics. The way that it works is that from 0 to 19, you use a very similar process. Each digit simply adds up using the three symbols. 1 dot equals 1, of course, and you just add dots all the way up to 4. And then you use a bar, which equals 5. When you add a dot to a bar, you get 6. 2 dots in a bar equals 7, and so on up to the number 9. You just add the symbols together. Then you get 10, which is 2 bars, and then you count to 14 by adding dots. 15, of course, is indicated by 3 bars. You simply add dots all the way up to 19. Now this is where it gets a little tricky, and this is where some of the stacking methods come into place, which is very important as a concept to indigenous mathematics in Mesoamerica. When a single dot is stacked upon another digit, you're counting from 20 and beyond. When they're stacked on top of each other with a large space between them, this changes the calculation through symbolic placement. Think about how in our Western mathematics, we stack numbers all the time, which changes the value. For example, think about a fraction. A lot of people are confused because they see a single digit on top and they say, how can that be equal to 20? I thought that that was equal to 1. But the difference is, of course, is that these numbers are stacked with a large space between them. Look at the numbers 6 and 25. They use the same symbols. The difference is that there is a large space in the middle for the number 25. The indigenous student would have learned this symbolic reference early in their education. Now, when the single digit is stacked and placed on top, that is always used to indicate the number 20. The top level dots always indicates a 20 base system, and the bottom level equals single digits up to the number 19. Okay, so a dot on top with 3 dots on bottom equals the number 23. A dot on top and the number 19 on the bottom equals the number 39. The indigenous people of Mexico and Central America used what is called a vigesimal system, or a 20-count system, which is different than ours. We use a 10-count system, of course. If we remember the previous diagram, we noted that 1 dot on top and 1 digit on bottom equals 20 plus the digit. So in this case, you have 2 dots on top. Each dot equals 20. So this number right here is 40. So again, on the top, each dot equals 20. The bottom level is a single digit. Okay, so this number right here would be 41, and so on. If you think about it, 4 dots on top would equal 80. and a bar on top would equal 100. Okay, let's look at a more complex equation. Going outside of the single number counting system, which we just went over, you can make equations to get larger numbers. This equation right here would be read from the bottom up as the arrow indicates. Also, the Mesoamerican student would not have seen the box. They would have only seen the numeric symbol. But the box helps us to visualize the numbers since we're not used to this system. Here we have a very basic equation that would be on the level of something like pre-algebra. Each level represents a different power of 20. In this equation, you have addition, you have multiplication, and again, you have stacking. So each level, as I mentioned before, goes up by various levels of 20. Each box has a simple number. The first one is 13, the second one is 5, the third one is 16, the fourth one is 1, and the fifth is 9. So the equation could continue going up. Okay, but as I said before, each level has a different function. The first level equals only the number displayed. Always. You do not need to do anything else with the first level. You just leave it alone. Whatever number is displayed there, that is the number that you come away with. However, in the next level, the vigesimal system comes into play. You multiply each level by various degrees of 20. So in the second level, you take the number displayed and you times it by 20. So in this case, it would be 5 times 20, which equals 100. The third level equals the number displayed times 20 squared. So in this case, you have 16 times 20 times 20, which equals 6,400. In the fourth level, it equals the number displayed times 20 to the third power. So in this case, it is 1 times 20 times 20 times 20, which equals 8,000. And the fifth level equals the number displayed times 20 to the fourth power, or 9 times 20 times 20 times 20 times 20, which equals 1,440,000. Okay, so as you can see, each level has a different function. All right, so let's just get the answer for each level. So you've solved the equation for each level, but you're not finished yet. Now you simply have to get the sum of each level by adding them together. Okay, so to help us visualize it, that is 13 plus 100 plus 6,400 plus 8,000 plus 1,440,000. And the sum and the answer to this equation is, of course, 1,454,513. And that, folks, is how you solve an indigenous math equation.